So the discovery of fission. In the mid-1930s, Enrico Fermi attempted to synthesize a new element. So scientists are curious and often try to do some maybe outrageous sorts of things, but that's how we discover new things. Scientific research does not always have to be practical. So he's trying to make a new element. He took uranium and he bombarded it with neutrons. So you get this setup where you're shooting neutrons at the uranium. The idea was, if we take this uranium and we throw neutrons at it, maybe we can get the neutron to stick. And then this unstable nucleus would undergo beta decay, where that neutron would get converted into a proton, and we could make a bigger element than uranium. Uranium is the most massive naturally occurring element, so he was going to try to make one that was a little bigger. So he did detect beta emission, but he never actually chemically examined the product to see if a new element had been formed. I'm kind of curious about that myself. Why not? And then other people repeated his experiments, because that's what scientists do. They publish their work, and then other people read it and say, well, I'm going to try that and see if it works. They might be wrong. So Lisa Meitner, Fritz Strassmann, Otto Hahn repeated these experiments. They did analyze the products, and they found that the products contained several elements that were lighter than uranium. So the original hypothesis was incorrect. But this discovery changed the world. And this is a huge discovery. They had discovered nuclear fission, the splitting of the uranium atom. So by bombarding uranium with neutrons, they were able to split that atom into smaller ones. So the uranium atom split into barium-140, krypton-93, gave off 3 neutrons, and not really even enormous, ginormous amounts of energy. So this is fission. Fission is splitting apart of the nucleus. This works with uranium-235, which composes less than 1% of all uranium. Uranium-238 is the most common isotope. It does not undergo fission. Only uranium-235 does. So you hear in the news sometimes, and they're talking about different countries, and they're worried about the amount of enriched uranium that they have. You have to have enough 235, uranium-235, to make bombs. Just regular uranium won't cut it. If you have a sample rich in 235, it can undergo a chain reaction. So you bombard the first nucleus with a neutron. It splits into barium and krypton, releasing 3 neutrons. Each of those neutrons can strike another uranium nucleus and cause it to split into krypton and barium again and release 3 more neutrons. And each of those can go on, and so you get what's called a chain reaction, where the neutrons released from the first reaction trigger or cause 3 more reactions, and then each of those causes 3 more reactions. And it can quickly grow out of control and become a huge explosion. So you need a critical mass of uranium-235. So you can't have, well, I suppose you could have it, but it would be incredibly difficult to obtain, a sample of uranium that was pure uranium-235. It's going to, if you just dig up some uranium somewhere, it's going to be mostly uranium-238, which isn't going to do anything. Less than 1% is uranium-235. So you can enrich it, you can get the ratio of uranium-235 to 238 up higher, but you're not going to get pure uranium-235 unless you expend a tremendous amount of money and effort. You have to have enough, though, in order for this reaction to be self-sustaining. Because the neutrons that are released here, if they're just going off and hitting uranium-238 atoms, they're not going to do anything. There has to be a high enough concentration of uranium-235 for them to continue the reaction. That's what a critical mass is. This reaction has been used to make atomic bombs. And we all know what happens when you set off an atomic bomb. Stuff like this mushroom cloud. So, the United States was afraid that Nazi Germany would develop an atomic bomb first, and so they started the Manhattan Project in Los Alamos, New Mexico. First nuclear weapon was detonated there in 1945. It had a force equivalent to 18,000 tons of dynamite. I mean, just one stick of dynamite will do some pretty significant damage. 18,000 tons of dynamite. Germany had already surrendered at this point, but we were at war with Japan, and so we dropped 2 bombs on Japan, killed 200,000 people. So, any questions? Yeah?
How does this tie into, you remember how you said radiation exists like naturally?
Yes.
So I know that there's stories about the radiation that happened in Japan and Godzilla and all that.
Mm-hmm.
What about that? Like, was it the radiation that they have from the uranium-235?
So the radiation is naturally occurring, but it's at a very low level. And so after the bombs were dropped on Japan, they do release a tremendous amount of radiation as well. The initial damage is all from just the release of energy. I mean, the force just blasting flattens things, right? Just like dynamite would do. But then there's also the after effects of all of this radiation. Some of the products of the reaction are radioactive, and then some radiation is just released as well. Those levels are going to be much higher than naturally occurring radiation. And as tragic as the detonation of those bombs was, scientists did make use of the situation and learned a lot about the effects of radiation on humans and other living organisms. And so we'll talk in a minute about radiation sickness and how, being exposed to radiation damages important molecules in your body and messes things up. It can kill you, or it can just give you some pretty nasty side effects. Mm-hmm.
Is there any way to contain radiation?
Radiation can be contained. Even gamma rays, which are have the most penetrating power, can be stopped by very thick slabs of concrete or several inches of lead. So that sort of radiation can be contained. Yeah.